My name is Eran Maimon. I'm the CTO of SolarPaint, and we try to find simple solutions to hard problems. So our vision is to transform outdoor surfaces into environment-friendly solar systems simply, cheaply, and aesthetically. So what's the big problem? Well, we want energy. Well, some of us more hippie kind may think that we don't need more energy, but we want it. We want to get from place to place. We want to maybe party or continue our daily life after the sun has set. And once we are billions of people, like 8, 9, 10 billion people, we need to feed them, and that takes a lot of energy. So what's the problem? When we come back home, we turn on the lights. They come on, right? No problem. No problem for us. We don't have a shortage of energy. And when you look at a graph of demand and supply of energy since the beginning of the Industrial Revolution, more or less, and you extrapolate to the future, you see, okay, when we want more energy, we supply more energy. We just pump more billions barrels of oil, and we make more energy, and we use it. But that's true only to a certain extent, and when we go further to the future, we start to have a gap. And when we have a gap in supply and demand, well, you better be rich if you want the lights on. Even if you're rich, not always it's sufficient. So, okay, we are mankind, we are anticipating the problem, and we try to solve it. And we already have a lot of other energy resources, such as solar, wind, biomass, etc. So let's look at the energy resources that are available to us. On the right-hand side, we can see all the non-renewable resources. The size of the circle is the amount of energy that you can get from this resource. On the left-hand side, you can see all the renewable resources. Okay? The difference is these are what we have for a lifetime, and these are regenerated, so that's per year. So we can see for coal, for example, we have a lot of coal, 900 terawatts year, which is a lot of energy. It could supply us for several decades, but eventually it will run out. And even if they find more, it will run out maybe a bit later. But when you look at renewables, well, there is one big circle here that is overcoming all the rest, and that's the sun. It overcomes all the other energy resources combined. And if you look at this small circle, that's what the world uses each year, 16 terawatt. So the difference in sizes is equivalent that in the fact that on a single day, the sun provides 3 times more energy than the world is using in a whole year. Okay, that's enormous amount of energy. So, okay, so we should use solar energy. There are 2 main kinds of solar technologies that are used today industrially. The first one and the oldest is solar thermal. Most of us, at least in Israel, we have solar thermal water heaters on our roofs. And also we have some plants that produce electricity. How? Most of us played with magnifying glasses when we were kids, and we burnt paper. If we weren't too naughty, we burnt only paper. And the idea here is more or less the same. You have a huge field of mirrors. You concentrate it to a receiver and heat a working fluid in a heat machine. A heat machine, ideally a Carnot machine, if you want to calculate the efficiency, it depends mostly on the temperature, the high temperature that you can reach at the receiver. The higher the temperature, the higher the efficiency. Okay, the second most common technology to harvest solar energy is solar photovoltaics. Here we transfer the the radiative energy of the sun straight to electricity without going through heat before. The idea is to take a semiconductor, mostly silicon, but not only, dope it with dopants to create a p-type and n-type semiconductors, and then you have something that's called a junction. The junction doesn't allow positive or negative charge carriers to cross. When a photon hits the junction, it creates positive and negative charge carriers, and they want to recombine, to come together, plus and minus, they are attracted. But they cannot cross the junction, and so they have to flow through the electrical circuit to recombine, and that's how we get current. If we want to calculate the efficiency of a solar panel, what we do is we multiply the voltage by the current at the maximum power point, that's electrical power, and we divide it by the power that is coming in, the radiative power from the sun. And right now, this technology surpasses the old technology of solar thermal. It's recent, in the last 5 years maybe. And if we look at the history, since its invention in '76 of solar photovoltaics, we have different families with different colors of photovoltaic devices. And you can see the improvement over the years of all of them. The best and most exotic ones, the multi-junction solar cells that are very expensive and used in space application, they reach almost 50% efficiency. Most of the solar cells that we are seeing on our rooftops are around here, 18%, 20%, more or less. And you can see also the newcomers, new technologies that come, and the improvement of them is very rapid, and we are approaching the 18% standard. So the sun is the solution, is the answer to the problems, but there are still some problems. What are the problems? Well, the sun is a great resource. However, the energy is dispersed. Actually, on 1 meter square, you get only 1 kilowatt of electricity. And when I say 1 kilowatt, I mean in Israel, in the summer, at noon. Okay? So it's not a lot of electricity if you are measuring it by square meter. Fortunately, we have a lot of square meters around the world, and you saw in the picture. So what people are doing? Well, they use the surfaces that they can. Okay? They put solar panels everywhere, and even in remote areas. You can debate how green it is to fill the desert with, or not the desert, with solar panels or with silicon pieces. But anyway, it creates electricity, which is nice. If you take it closer to where people live, well, then you come to the prices of real estate and other problems. At least you don't have to carry the electricity so far, and that's also expensive. So basically, these technologies have some inherent deficiencies. First is the huge open areas, as we saw. The second is the high installation cost. They take a lot of steel to just to put them in place. And third, well, even if we try and do some dual use of surfaces like on rooftops and that are not used for anything else, well, 50% of the rooftops are not adequate to carry this. They are just too heavy, 18 kilos a piece. So this is a big problem. But imagine, what if we could turn any surface into a solar harvesting device, merely by painting it? You can think of street lights, of rural housing, of city towers. Maybe a Boeing jumbo jet you cannot really fly on any solar. But small planes maybe you can. And the big thing, roads. Roads are just enormous stretches of area that is already taken by mankind, and usually it just warms in the sun. So it could have been very nice if it would warm just a bit less and create some electricity. Now, those of you who have very good eyes can see the power lines that go along the road. Actually, it's not a surprise, because usually they first build the power lines, and then they pave the road on the service route of the power line, because the electricity was there first. So can we do it? Well, if you look at roads, the example of roads again, if you take 80,000 square kilometers in the US highway system alone, and you multiply it by a modest 5% efficiency, you get 8,000 terawatt hour per year, which is equivalent to twice the amount of electricity produced today in the US. And that's an impact, okay? So can we do it? Well, that's exactly what we are doing. So I'll show you a short 2-minute film.
Demand for electricity is on the rise. In the field of solar energy, significant land resources are a necessity for all types of solar applications.
What if we had a cheap way to generate electricity out of any object exposed to sunlight merely by painting it? Think of the vast stretches of roads across the planet which just sit and warm in the sun. Think about irregularly shaped buildings, walls, roofs, anything that is not suitable for the bulky solar panels.
These thoughts led us to the disruptive concept of SolarPaint. Our vision is to become world leaders in the field of thick solar coating and to transform any object into a functional solar panel.
We deploy simple pre-treated netting, much like a mosquito net. Once in place on a designated surface, a special paint is applied, infused with nanoparticles which are specially grown in our labs. The pigments are based on inexpensive, stable oxides. Rust doesn't rust. Once the paint has cured, all that is left to do is to connect it to the peripherals just like any other ready-made solar panel.
Recent progress in wet chemistry-based nanofabrication techniques enables us to benefit from relatively low R&D costs while having the ability to upscale production quickly.
Our R&D efforts are underway to fulfill our goal of turning any surface into a solar panel in an aesthetic, inexpensive and efficient manner.
SolarPaint has multiple applications, from streetlights to transportation, buildings, infrastructure, and many more. It has relevance both to the solar energy market as well as to the paints and coating market.
With its huge market potential, SolarPaint is well positioned for commercial success and for making a large contribution to society's struggle to reduce reliance on global fossil fuels. We are excited by our new technology and invite you to take part in this revolution and paint a brighter future.
Okay, so this is small us, and to make this come true, what do we need? So basically, what we get from the sun is photons at a different spectrum. Starts from the UV, the highest energy, then through the visible, and down to the infrared. Okay, each photon carries an energy with it, and the closer we get to the blue and UV, the higher the energy. Now, if we take a semiconductor for use in photovoltaic applications, the most important property of the semiconductor is the energy band gap. The energy band gap decides which photons can be absorbed and which cannot be absorbed. So if we look at this graph, we can see the usable electric power that is dependent on the energy of the band gap, which decides which photons we can use and which are below the band gap and are not usable, and which are above the band gap and we lose some of the energy to the band edge. So what we are looking is something here in the range of 1 to 1.5 electron volt, which may give us the theoretical maximum that we can get from a single junction solar cell. By the way, silicon is around 1.1. It's here. So you see it's very usable. So when we came to choose our materials, we had a certain criteria so we can make this solar paint. The first is that the material should be stable, meaning that it should be in the material should be in the lowest energy state, like oxide, for example, and so they don't rust, I would say. Second is that the materials have to be abundant. There have to be a lot of these materials on the Earth's crust because we need a lot of them. Third, obvious, cheap. 4, it should be solution processable, so we can make paint out of it, meaning that it has to be suitable with common industrial techniques like roll-to-roll, like airless, brush spraying, etc. And the 5th, it should be efficient enough, maybe not 50%, but enough to be commercially viable, meaning it has to have the optimal band gap, good electrical properties, and suitable contacts. Those were in our minds when we started the search for our materials, and what we have now is a nice prototype that you can see. Here we are painting our electrodes with our SolarPaint, and this is how it looks under a scanning electron microscope. You can see a nice coverage of the electrodes, and you can see here this is our 3rd prototype, which we measured earlier today, and we got nice results of electricity. So we start to function. It's really nice, and our next step would be to get a commercially viable efficiency until July 2016, and we hope to start sales by the beginning of 2018. So that's it. Thank you very much.